give.
Madam, I think
Yeah.
we should wait 5 minutes. No one else is here.
Okay, okay, yeah, we should wait for 5 minutes. Let's wait for 5 minutes and let's see them. Yeah.
Okay.
Okay. Hello. So I think we should start the session now. So Ramzan is also going. So we should go. So it's fine. Am I audible?
Yes, ma'am.
Okay. Thank you for letting me know. So I think week 11 content is also live now. Through Aditya sir, and only 2 weeks left. So we will complete this course as soon as possible. So let us start this. So in this particular week, the sir especially focused on some probability concepts and some of the concepts related to probability used in communication system like DPSK and PSK. So some concepts I want to let you know so that you don't have any issues with that. Full screen. Yeah. So the information is the information is inversely proportional to probability. Information is actually defined as the knowledge a particular uh, communication system have. So this information is directly proportional to probability, and if I is equals to information and P is equals to probability of occurrence, then I is equals to log 1 by P, which is defined in terms of bits. And information contained in any communication system is defined in terms of bits, and I is equals to log 2 1 by P. If log 10 is there, then it is defined in terms of Hartley, whereas log 2 is there, then it is defined in terms of bits. And similarly, the entropy, how will you actually use the information contained in any communication system? So we usually using our entropy. So every information is called entropy, which is defined as the bits per symbol. So the formula for the entropy is H is equals to summation of I is equals to 1 to N Pi log 1 by Pi, where Pi is the probability of one symbol. Probability of ith symbol. So let us see some example of that. So a source can get 4 symbols with probability 1 by 2, 1 by 4, 1 by 8 and 1 by 8. Calculate the entropy, and entropy when the symbols are equal probability. It means the probability will have equal probability for probability of 1, probability of 2, probability of 3, probability of 4, which is equals to 1 by 4. So how will we calculate? So using this formula to calculate it, it is 1.75 bits per symbol. Whereas when it is equal probable, we calculate it as a 2 bits per symbol. So whenever we see, the conclusion we draw from here is whenever we take the symbols with equal probable events, then the entropy calculated means every information contained in the particular system is higher. So here we can see it is 2 bits per symbol, whereas here you can see it's a 1.75 bits per symbol. Now, so Shannon-Fenner algorithm is one of the algorithms to decode and encode the symbols so that you will have a better information rate. And information rate is defined as R into H. H is entropy and R is a rate. So symbols per second and bits per second per symbol. Similarly, you can define it for different symbols. For example, you have source which generates 3 symbols with probability this at the rate of 3000 symbols per second. What is the average rate? So average bit rate you have to calculate, which is IR. So H is equals to this one, 2 you are getting. And note, entropy increases with number of symbols, which is log n. And entropy is maximum for equal probable events, while entropy decreases or increases when when only the probability improves. For example, entropy H always decreases when we don't have equiprobable event. Probability of symbols gets different. So here it's very good channel capacity formula, which is C is equal to B log 2 1 plus S by N. S by N is a SNR and B is equal to bandwidth. It is a signal to noise ratio. So you have to observe that for error-free transmission, RB is always less than or equals to C. RB is the maximum rate achievable for any communication system. Here communication system I am referring to H. H means transfer function of the communication system. Here you have input X and Y. So it can be in terms of T, it can be in terms of S. So here also, if we take the example of this one, the bandwidth allocated to a particular communication system is 5 kHz, it is B is 5 kHz, and signal to noise ratio is 15, S by N is 15. Calculate the channel capacity, and if the signal to noise ratio is 31, calculate the bandwidth. So how will you calculate? Using channel capacity 7, which is C is equals to B log 2 1 plus SNR, S by R, and you have calculated using this. So moving ahead, I just want you to have the understanding of probability of error. So see, the probability of error, which is the optimum receiver, the threshold in optimum receiver, you have the threshold changing. So P of E is equals to P1, which is the probability of transmitting P1 with error associated with it. For example, you transmit 1, but you are getting 0. So P of 0 divided by 1 plus P of 0 into P of 1 divided by 0 means probability of 1 with probability of error of 1 plus P of 0 into probability of error of transmitting 0. So this is error. For example, 2-bit scenario. 2 bits you are transmitting at the transmitter, and at the receiver you are receiving 2 bits. But what is the probability of transmitting 0 and you are getting also as 0? This is represented by P of 0 by 0. And what is the probability of transmitting 0 that you are getting 1? It is represented by P of 1. You are receiving 1 but transmitted 0. So this is error associated with 0. And if we transmit 1 and we are getting 0, then this is error associated with 1. P of 1 divided by 0. So, and what is the P of C, which is a no error probability, which is equals to 1 minus P of C. P of correctness. P of correctness. So these are known as crossover probability, which is also called error probability. And if you plot it, the density function, which is a PDF of error function. So you have observed that these are always Gaussian in nature. Can somebody tell me why we every time we take the Gaussian function? Or do you know the central limit theorem? Any of you?
No.
No. Okay. So, KG sir, have you heard of the central limit theorem?
Yes, madam. It says something like this. If you take samples from a Gaussian distribution and the average also is a Gaussian distribution, samples average, and something like that, because
No issue, no issue. At least you know a little bit of it. Kushit, I think yeah, this is a very common question of interviewers. So they used to ask the central limit theorem. So a central limit theorem says any distribution, either it is Rayleigh distribution, Racine distribution, Gaussian distribution, and Poisson distribution, and many types of distribution exist, uniform distribution. So those distributions, their average After a very long, when n tends to infinity, average is what? Average is so central limit theorem. So I just want to ask one thing, like the noise is coming or not? Just like I'm using this mic, I want to know. Hello.
No noise, madam.
Okay. Okay. Nice. So yeah, so central limit theorem. If you have any random variable which is x and it is distributed in nature, suppose it is Poisson distribution. What is the Poisson distribution formula? E power minus lambda into x divided by lambda factorial of this x of lambda. Here lambda is mean. I'm not sure if this distribution is correct or not. E power minus lambda divided into x divided by lambda distribution. Yeah, lambda is mean. So suppose this is correct, I have to check. But yeah, suppose if it is correct, then this if you calculate the expected value of x ranging from n is equals to 1 to infinity divided by n, suppose n, limit n tends to infinity, then this converts to whatever distribution will have some distribution. It is found that it is Gaussian in nature. So this is not a case with only Poisson distribution. It is a case with every other distribution, really ratio. So in communication system, so that's why every time we take everything to be a Gaussian distribution, because after some point it will behave like a Gaussian distribution. And if you see, the Gaussian distribution is nothing but somewhat related to this exponential function. Can somebody tell me what is the Gaussian distribution formula?
1 by 2 pi sigma e to the power of minus x minus average x minus mu whole square by lambda by sigma square. Yeah, correct.
Yeah, this one. So this is f of x, which is a function of mu and sigma. And nice, sir, you know these things. It's very good. So this is mu. This is what 2 sigma. It's up to 1 by root 2 power. It's 1 by root 2. So yeah, this is the point at which the Gaussian distribution is symmetric with respect to y-axis. This is known as mean, and the variation up to which the power decreases to 1 by 2 times of the power, then it is called that value up to that value is called this standard deviation. So sigma is a standard deviation, and sigma square is variance, like how the data sets are varied. So this is what the central limit theorem says. So similarly, the error, we are assuming it as a Gaussian distribution, and each error will have some mean and variance. So suppose it is having the mean of a0 and it is having the mean of a1. So how will you calculate the p of error? So p of error is actually the p of 1, the probability of transmitting 1, and you are getting somewhat different values. So probability of z, which is we are representing it as a 1. So this is error probability distribution in multiplication of tz. So minus infinity to VTH. Suppose VTH is this one, VTH. Then minus infinity to VTH, you are getting 0. Okay, so you should know, you should get 1. So here you are integrating with respect to dz, and similarly for p0 from VTH to infinity, it should have some value related to 0. So if you are transmitting 0, but you are getting a higher value up to greater than that threshold. So for example, if we can say this is value, this is value. If you are transmitting 0, suppose this is 0 and this is 1, and if you are transmitting 0 but you are getting 1, so up to some value you are representing that to 1, so you are transmitting this to VTS to infinity. VTS means the value to threshold value. So this is how you calculate the probability of error, and this is calculated for every BPSK modulation, ASK modulation, QPSK modulation, and COM. So how will you calculate the probability, minimum probability of error? If P of this differentiation of P of E or divided by P Z with respect to Z, because it is distributed in Z domain, then how this error will be minimum? So this criteria should match for getting error to be minimum. One sec. Okay. Yeah. So this criteria should be should be satisfied in order to have less probability of error or minimum probability of error. So this is central limit theorem, and then if this probability of transmitting 1 and probability of transmitting 0 is same, then this should have the same threshold. So this should have the same threshold, and this is called map. So this is maximum of superior probability criteria. I don't know what is the full form of this. Map full form.
Maximum posterior no.
Posterior
No.
criteria, maximum posterior criteria, and if the probability is same, then it is called maximum likelihood criteria, ML criteria. So sorry, I have mentioned also a posterior criteria, maximum map. So when P of 0 not equals to P of n, so how will you decide which symbol is transmitted? So from here, everybody is aware of the fact what is ML and AI. So everyone is going towards ML AI. So map and ML is the basis of ML AI. So somebody wants to learn ML AI. So from here everything gets derived. So the MLAI is no more different from communication system and probability concepts. So communication system is nothing but a probability formulations, how you can formulate. And now we're in research also, people are applying MLAI in this particular domain. So for map, how will you decide which symbol is transmitted? So if P of 1 into P of Z of 1, say this is error, is greater than P of 0 into P Z of 0, then symbol 1 is transmitted because this is greater. For example, if symbol 0 is transmitted, then P of 0 into P of Z0 is greater than P of 1 into P of Z1, then symbol 0 is transmitted. For optimum threshold using ML decoder, this one is same, and then VTH is simply the symbol sum divided by 2. This is derived, or you can also derive, but for map it is different. So how will you derive? So this is the function of Q of A1 minus A0 divided by 2 sigma. So now let us see a BPSK constellation is corrupted by noise having PDF is given as in figure. So I wanted to know whether sir has taught these things or not. KG Krishna sir?
No, I have not seen the videos, madam. But one thing I tell you is I have done personal communications too in the last semester. All these things are covered: QPSK, BPSK, and all that.
Nice.
So, but I have just gone through.
Yeah, Kurshid.
Ma'am, actually, this is all part of that second part, digital communications only. This has not been covered in any of the lecture. And this map and this ML, right? Maximum likelihood receiver and maximum a posteriori criteria. We only know about these terms only, not in this much detail.
Okay. But yes, the week 11 and week 12, sir was covering probability concepts now. So what was that? what sir has covered? Can you tell me?
And sir is actually sticking to the basics of the probability, and then he's giving us application involving what has been taught to us and related to this analog portion only, analog communication
Yeah,
only.
some
Oh,
symbols, if the symbols are transmitted, and what is the
So he's
probability
actually
that
avoiding all this digital thing.
something like that. When symbols are transmitted, what is the probability that they these to go on error? Those kind of things, but mostly on probability, not on
okay, not on communication system.
yeah.
Okay. So these are the part of digital communication. So map and memel are part of digital communication. So I thought that sir has taught this thing, but otherwise it is fine if sir doesn't taught this thing. So we can leave this thing. And but yeah, if you want to learn about ML and MA map, so it's a very good thing. And mostly they their favorite questions of interviewers, they usually ask from central limit theorem and these things. So it's okay, sir has not taught, so we can leave this thing, otherwise it's fine. Random variable sir has taught this. So do you know what is random variable?
Yes, ma'am. Random variable. It's random in nature and it is defined by its probability distribution function.
Random variable is okay. So can you tell me in terms of function?
Sorry, ma'am. In terms of function,
Yeah.
no, ma'am. There is no function. Actually, we characterized it by using this probability distribution function. It is of different type. Some is exponential distribution. Some is different sort of distribution.
Okay. So I'll define this random variable. So random variable is actually a function which maps the output of the sample space to a real number axis, real line axis. For example, you have domain, you have range. So yeah, sometimes it is very confusing, and we cannot define it in a very easy terms, like it's random in nature, and we'll have the probability distribution function and those. So how it has come from? So I think sir has taught this, so I am dealing with this. So random variable is actually a function which maps the output of any sample space to a real line axis value or real value. So here you have sample space as suppose 1, 2, 3, 4, 5 and 6. Okay, so you are mapping the even, suppose random variable x, it maps even output of a dice to 1, and maps odd output of a dice to 0. So suppose you have 1, 3, 5, and it will all map to 1 value, and 2, 4, 6, it will all map to 2 value. So this mapping is called random variable x. For example, let's take more example, h and t. So if head occurs, then it maps x1 maps to 1 and x to 1 and t to 0. Okay, t to 0, or somewhat we can also map to -1. It's okay. So it is x1. So how we will write this x1 and x? So we will write x as a function which maps 2, 3, 4, 5, 6 to 1 and 2, and x1 is h t to 1 or -1. Okay, so how will x1 write? So x1 is having this h is equals to 1, x1 also having t is equals to minus 1, and x is having 1 as 1, x1 is having 3 as 1, x is having 5 as 1, and x1 is having 2 as 2, and x is having 4 as 2, x is having 6 as 2. Okay, so this is what the random variable does. And these, the domain of a function, this is called domain, right? Function. And this is range. So range is always real line, any value of real line, and domain is always the output of a sample space. So this is what the random variable does. I think it's clear. So since it is a function, this x1 and x2, it's a function. So how we will describe it? So you will have the density function, how it actually varies with respect to different values of x, different values of input. So that's why f of x1 is there, which varies like this, which varies like uniform distribution, which varies like, suppose this is x, f of x1, this is x1, this is x1, and these x1, these are taken from the sample space, which is output of any random experiment. So that's why random name is there. So output of any random experiment, and this is x1 values, x1 values, x1 values, this is x1. Okay, and similarly f of x, suppose this is varies like Rayleigh, how the Rayleigh distributed values, it's more like this one, of e power minus a square by 2a. So here x square by 2a, where a is exponential component. So here, so this is actually what is a random variable, and this is x1 and x is a random variable. Hope this is clear now.
Madam,
Yeah.
what I suggest is, in fact, this is a little abstract. Maybe you can take some examples, and then we can connect. Actually, that's
Okay, we'll take some more examples.
We can focus on the problems, because actually what I find is I took a course on probability theory like Borel set, sigma algebra, but really gone above my head. There is electrical engineering course.
So yes,
but when I see the actual applications, problems, it's very easy to connect and do it. Okay.
Yes, yes.
So I suggest maybe we should look at some problems which are going to come in the assignment and all that. That will give us a lot of insight.
Yeah. So I have taken the problems at the last, but yeah, sir. So basically, in order to learn the probability, you should know the classical definition and the theoretical definition and how these are connected. So in the last class, I guess I told you about the Borel set sigma algebra. I think most of the class students didn't get that point, which I am trying to actually tell that. So since it is not even covered in this course, so I didn't focus much on that. But yeah, I just really want you to please look at the basic definition of random variable and what is the significance of what is called fields, and the Borel field, sigma field, and how this has come.
Yeah, madam, one problem with that is when you get into theory, they give concepts like measurable and countable infinity.
Yes.
That really is a different way of imagining things. But as far as communications is concerned, I don't think we apply so deep all that. Maybe
no, sir. If you go into since I am a research scholar in this field, so even if I have to write a single paper, then it's like you have to use all the concepts of probability theory, starting from the Borel's fields, Lagrange multiplier, Lagrange multiplier and Lagrange, what is that? I'm not remembering. But yeah, applies starting from basics of probability to the end of BER, SNR, spectral efficiency, and those things. So in fact, I think today Narendra Modi sir has visited Hyderabad. So I think he's going to talk on the 5G data rates, development scenarios. Yeah,
Yes, madam.
are you
Very.
aware of that fact, sir? Narendra Modi sir is going to visit today. I think he has come
Yeah,
today.
maybe I listen on the TV.
You have
Yeah,
listened
like
him.
but
Where?
one thing, see, I even if you study that, the only thing probability distribution used in communications I found is a Gaussian. I
Yeah.
never found any Poisson, Rayleigh, nothing. Okay, most I think there is one more is used, Gaussian and Rayleigh. I don't know, but very less. But I am able to understand the application. So most of the time, when the problem is given, examples are given.
So you have given a very good topic of for preparation, like the distribution of the probability distribution and their application in communication system. I'll deal this in the next class.
Okay, sure.
Yeah, so that you get to know. And one more thing, sir, you are talking about the Poisson distribution now. So have you heard about this V2X communication? V2X.
V2X, vehicle to tower, vehicle to roadside tower communication.
Yes, yes,
Right.
yes, yes.
Yes.
So
Yes.
here, like in every case, we are dealing with the Poisson distribution.
Okay, number of vehicles approaching a tower. Something like
Ha ha ha. So my research is on 5G V2X. So I'm working in 5G V2X.
okay.
So like how the vehicles communicate with each other and share their information, and how their resource getting allocated, like power, bandwidth, and their transmission rate. For example, we have an emergency vehicle warning, then emergency vehicle comes in between, then emergency vehicles has given as a one first priority to transmit their local information, like vehicular speed, vehicular acceleration, gyroscope values, and like their location, especially their location, so that every vehicles in the surrounding areas gets aware of the results. So Qualcomm is working on it, and in fact in our Tihan test bed, which is IIT Hyderabad, is also working on it. So I must say that yeah, so in real life also we see this Poisson distribution, everything, Rayleigh, Raysian, Markov chain also. We always model the scenario using Markov field or Markov chain. So sorry, this is also called Markov decision process, MDP. So have you heard of this Markov decision processor?
Yes. This is a sequence of events. The probability of the next event depends on the state of the something like that. I heard. I heard all the terms. I heard, madam, but only 10% has gone into my head. I only familiar with the names.
Okay, nice, very nice.
Yeah.
So we saw these things in our real life space, but yeah, I'll deal with this probability distribution and their application in real life, so that I will have the understanding. But yeah, so
Yes.
these Borel sets and all, I think these are the concepts of probability. And so since the questions you are saying, I'll deal with some of the questions related to this. As of now, since many of us are not dealing with this, so whatever I have today, so I'll wait a second. Today I'll tell that, and I think, sir, using this explanation, are you like have get clear about what is how the random variable is called as a function? I want to know from all of you. Okay, Khurshid, are you here? Or you went? I think he went. Hello. Usha.
Yes, ma'am.
Are you getting the concept of random variable?
Somewhat, ma'am.
Okay.
Okay.
Actually, what you are saying, madam, random variable actually is not a variable; it is a function mapping. For
Yes.
example,
That's what I wanted to say. Yeah.
Yeah.
The name confuse us, but yeah, this is a function which maps the values from domain to range, and this is also having some restrictions. Can we have many to one mapping in function? Can we have one to many mapping function?
Oh, no. Many to one can't be.
No. Many to one is applicable, but when you have one to many, so this is not called as a function.
Okay, function. Yes.
Because here, see, we can see all the even values are mapping to one variable, and all the odd values are mapping to one value. Okay, other value. But when you have a different suppose one is also mapped to a one and two is also mapped to a one. So two different cases will exist. Then if you have the inverse mapping now, you won't be able to get as a domain. So this is not applies to function. This is even not applicable to function. So whenever you have one to many, so it is not applicable to function. So this is one of the case, like we cannot call this as a function. So this random variable follows all those properties of the function, all those properties of the domain and range criteria to be called as a function. So sometimes the names confuse us. This is a variable. Yeah, it is a variable, but it is also called as function which maps from one domain to another range. So this is this is all about random variable, and I'll deal with this. I think the probability distribution and their applications and their problems, associated problems. But so along with the random variable, we have some properties related to their expectation value and the central moments and the variance. So if you see the random variable, if it is constant, then expected value of the same random variable is same, because this expected value of x dash is a constant. Then if you have hello.
Yeah, if it is constant, then it is not called a random variable. It is deterministic, right? Yeah.
No. For a constant value cannot be called as random variable. How?
Because it takes only one value, that is a constant, that is a determinant.
Yes, then we know that it is not random then.
For example, if you like a normal algebra, if you say x is equal to 2, that is not random because we predefined it all the time, 100%. The probability of x equal to 1 is probability with 1. That is not random variable.
No. Yeah.
Any variable whose probability we declare it as 1, it cannot be random.
No, a constant value is a random variable or not. Just let me know this. Just think about it, whether it is random variable or not. Just once think about it. Random.
Yeah. Okay. So, for example, in the uniform distribution, for example, coin toss you take, head and tails are uniform 1 by 2, 1 by 2. So, if you define the coin toss, outcome of the coin toss as a random variable, it is constant 1 by 2.
Yes. So it is irrespective of the fact that a constant is also called as a random variable. So you have given here a very good example, but also we can see just sometimes we don't think about it explicitly. So let us see example of a dice. Suppose it is a dice having this probability of sample space 1, 2, 3, 4, 5 and 6, and to all values this x random variable 1, 2, 3, 4, 5, 6, the x random variable maps to a constant value which is 1 by 6. So x which maps s to 1 by 6. So this is a constant random variable. So it is called a random variable, right?
Yes. But that applies only to uniform distribution.
Yeah, it applies to uniform distribution, but it is called random variable. Yeah, it is a type of random variable. Yeah. So uniform distribution, yes, uniform distribution, where we have the in x-axis the outputs of the outputs of a random experiment, any random experiment. So it will map to a 1 by 6. So if you have a constant random variable, their expectation value is also the same value. So So now, how the expectation of random variable is defined? X fx, where x is equals to minus infinity to infinity. It is in discrete domain. Minus infinity to infinity x fx dx. You know this formula?
Yes, ma'am. Yes,
Yes.
ma'am.
Nice, nice. So here, if you can check with it, it will be the same. So if you can just take the example of dice, 1 into 1 by 6 plus, sorry, 2 into 1 by 6 plus 3 into 1 by 6 plus x is the possible values we can take from the domain. 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6. So 1 by 6, 1 plus 2 plus 3 plus 4 plus 5. I think I'm wrong or what? 3, 6, 5 plus 6.
Yes.
What is that? 3, 6, 10 plus 5. 6 plus 15.
No.
Why I'm not getting?
No. See, there are 6 phases. Each phase is equal probability. Each phase has equal probability. So 1 dot 1 by 6 plus 1 dot 1 by 6 plus 1 dot up to 6. 6 multiplied by 1 plus 1 plus 1 plus 1. So
No.
no.
I think
Yes,
expectation.
ma'am. It was correct. It was correct.
1 into 1 into 1 into it should be there. No, it should be 1 into
Yes,
2.
ma'am.
Let us take some example here, whether I have taken or not.
Yes, madam. This is a very challenging subject, madam. I failed twice. I took 2 courses.
No, I forget it actually. But yeah, it should take some value, not 1 into 1. It should have 1 into 2, I guess. But I think this is not, yeah.
No. What you have formulated is correct, but 1 by 6, 1 by 6 is correct. But the number 1, you see, the outcome of this, there is no meaning of average number, right? Either you get 1 or you get 2 or 3 or 4 or 5 or 6. There is nothing like average number.
Okay,
There
you
is,
are saying it is not like an average.
yeah. So,
Probability of a uniform distribution, sorry, expectation of a uniform distribution, you calculate expectation of uniform distribution.
uniform distribution is no, it is 1 by 6 only, uniform distribution. Any side is 1 by 6 probability only. So
No.
the meaning,
It is, suppose it is related to this A to B. I remember this one. And then it will be 1 by B minus A.
I tell you, I got an example, a good example to tell you. Let us say we are throwing a dice 1 to 6. Okay.
A plus B
So
by
for
2, yeah.
every one number, okay, one phase, we are betting on 1 rupee. For for betting 2 rupees. Then if you compute the way you have done it, so that gives us the average gain of how much money, probability of the average. The average gain. Okay. For example, I bet for phase 1 1 rupee, phase 2 2 rupees, phase 3 3 rupees, like that. Then what is my average gain or loss?
So, yes, sir, I want to continue on that. So, yeah, it is correct. So, when you calculate the expectation of this value, it will be 7 by 2 only. It is correct because here you cannot take 1 1 1 because here the possible x values with associated probability. This is the probability associated with having this x value. For example, here I took this wrong. This is not, it is a constant value. It is not the random variable. It is x bar. So the expectation of mean is equals to mean. It is a x bar is mean. It is not a random variable. So for example, it is a uniform distribution, which is x. It is distributing as a uniform from A to B. So you will have, the density function, the area under the density function, suppose x, it is fx, it should be 1, right? So if it is distributed from A to B, then the amplitude here should be 1 by B minus A. And if you calculate the mean of it, the mean is A plus B by 2, which is expectation, x bar. How you have calculated? Using the same formula, x bar is equals to x into fx dx. So let us calculate this, minus infinity to infinity. Here A to B, let us take this A to B positive only. So x is this one, or fx, the value is 1 by B minus A into dx. So this one, 1 upon B minus A, this is x dx. So 1 upon B minus A to B. So here if you say, this is x square by 2, A to B. So 1 by 2 B minus A, B square minus A square, 1 by 2 B minus A, B plus A divided by 2, B minus A. So this will get cancelled. You will have B plus A divided by 2. So x bar is this one. And similarly, if we plot this for our case, how it will be? 1 to 6 you have values, and you are mapping every value to 1 by 6, So it should be 1, 2, 3, 4, 5 or 6. 1, 2, 3, 4, 5. So you will have 6. It is 1 by 6. To this interval, 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 to this interval. Here we are taking continuous. Similarly, 6, and here it should be 7, because here we are taking it to a interval. So 1 by 6, here 1 by 6. And in here, this is 7 divided by 2. A plus B divided by 2. And if you multiply, A is 1, B is equals to, interval, no. Here should be 1 by 5, 6, and mean is x bar is equals to A plus B divided by 2. 1 plus 6 divided by 2, which is 7 by 2. I am also getting 7 by 2 using this formula.
Yeah, that is correct. That is correct. The way it is only in interpretation. For example, if you interpret as 1, 2, 3 as phases, there is nothing like 3.5 phase, right?
Yes.
So, but if you interpret as I am betting on phase 1, 1 rupee, the phase 2, 2 rupees, the average gain or loss for me is 3.5.
Yes. You interpreted it very in a nice way. So yeah, this is how the expectation value is calculated. Sorry for the confusion. Like if it is constant, then the average, the expectation is also same. But yeah, no. If you calculate the expectation of a mean, then it will be mean. Like in this case, this is mean. And if we calculate this is the properties of a expectation value. Properties. So expectation of this one is this. So expectation of, you can multiply this with a constant, then it should be C into multiplication of that mean of this random variable x. And if you calculate the expectation of the sum of two random variables, then it is simply the sum of two random variables, their expectation sum. So if it is also the same with this one, so expectation of x into y is equals to expectation of ex into ey. So I just want to know,
linear operator. This is linear operator.
Yes, linear operator. So when it is the case, when you will get this one, just think about it.
If x and y are independent.
Okay, nice sir, nice. So we know about this one. E of xy is equals to E of x into E of y when X and Y are independent. Why is this the case? Can you tell me, sir?
Ma'am, their probability will one event occurring will affect the probability of other, and so probability distribution function will also differ.
Okay, you have told in the form of definition. Can you tell me a simple the formula for the independent event?
A intersection B is probability equal to multiplication of the probability of all events.
Yes. So since you told me their intersection is equals to P of X into P of Y. Their intersection means and. So P of X into Y we also call this P of X into P of Y. And if you calculate this E of X, simply but X into P of X minus infinity to infinity. E of Y is equals to minus infinity to infinity. Y into P of Y. So if we calculate P of x y is equals to simply P of x y, which is equals to P of x y x so minus infinity to infinity, y is equals to minus infinity to infinity. This is simply but x y into P of x into P of y, which is equals to minus infinity to infinity, y is equals to minus infinity to infinity, and which is simply the multiplication of E of x into E of y. So this is why this is when x and y are independent. Only when x and y are independent. One more thing. What is the value of P of x intersection y when these are mutually exclusive?
When mutually exclusive.
Yes.
X and Y. Then this is phi. Nil event. We will not get.
So x and intersection y is phi and it is 0. Okay.
And yes, probably.
So yeah. So this is the difference between mutually exclusive and independent events. So when the independent events are there, then their occurrence will not even affect or it does not care about the other event occurrence. And when these are mutually exclusive, then if occurrence of one event restricts the occurrence of other event. So their intersection should be equals to phi and their probability should be equals to 0. Now, moving ahead. So this is.
Can you tell us some practical example of that?
Yes.
This one practical example of this. Expectation of x y equal to expectation of x into expectation of y when they are independent. So some practical example.
Yes. For example, you have two trials, and in one trial you have sample space 1, trial 1, and in second trial you have sample space trial 2. So if you have trial 1 and trial 2, this is one dice and this is second dice. You have here 1, 2, 3, 4, 5 and 6. Here you have 1, 2, 3, 4, 5 and 6. Let us denote this as 2, 2, 2, 2, 2, 2. Let us denote this 1, 1, 1, 1, 1. So here you will have sample space as this one. Here you will have sample space as this one. The domain is very different, these two. So their intersection will simply the multiplication of these two. For example, consider the second example. Example 1. Example 2. You have one trial and you have one experiment S1, S2. Here you will have even 2, 4, 6. Here you will have odd 1, 3, 5. So S1, S2 will lies in the same domain. Here we will have 2, 4, 6. Here we will have 1, 3, 5. So if S1 occurs, it restricts the occurrence of S2. And if S2 occurs, it restricts the occurrence of S1. So this is an example of mutually exclusive. Sorry. Because they don't have any intersection, right? Mutually exclusive Here probability of S1 intersection S2 is 0. S1 intersection S2 is 5. But here their probability S1 S2, their probability P of S1 intersection S2 simply multiplication, because it does, this doesn't care, there's having different sample space itself, the sample boundary. So P of S1 into P of S2. And this is also the case of E of expectation of intersection E of X into E of Y. So this is naturally occurring events, and this is what the independent events. So in general, in the base theorem also we considered mutually exclusive and exhaustive. One other term comes into the mind, which is exhaustive. What is that exhaustive? Tell me whether this event is exhaustive or not.
Exhaustive means when both event taken together, union will give us the sample space.
Total sample
So-
space. Yeah.
Yes, ma'am. Yes, ma'am. So here we have taken 2 courses. No, ma'am, not. It is not exhaustive.
Yeah, when 1 to 6 and also includes null, then it is exhaustive.
No, it is exhaustive. Example of exhaustive now, because the experiment 1 and 2, S1 union
Union.
S2.
S1 union S2.
Okay, then, ma'am, then it is exhaustive.
Yes.
Yeah, so here you will have the exhaustive events as well. So whenever we talk about the mutually exclusive, the exhaustive we have to also check, and the independent events are different case. Like you have head tail, you have two different coins. You turn this one coin and you turn this two coin. Whether the tossing of one coin affects this occurrence? No, because if even and second case, when you have only one coin and tossing, and you consider H and T. So H and T are two different events, and their union will correspond to total sample space, and that events are called mutually exclusive but not independent. But when two coins are different and you are tossing independently, even in fact the term also has some meaning, which is independently, then it is called independent events. I think it's clear now.
Madam, in
Yes,
my college days, I think long back, 40 years ago, we learned about this independence using a gambler's fallacy. I don't know.
Yes,
whether-
yes.
Yeah. So what he used to say is, yes, there is a die. Okay, 1 to 6 die. Okay. So you first you bet is 10 rupees. Okay, 1 rupee you bet. Okay, one number. Okay. So let us say whatever number, it doesn't come. So the next what they say is you double your bet next time. It doesn't come. Then third also you double your previous. First time 1 rupee, next time 2 rupees, next time 4 rupees, like that. So what people used to say is, at some point out of 6, at least one should come, right? 1 of 6. They say, as you keep increasing your bets, so your chances of you are moving towards chances of winning. So you are bound to gain something if you provided you keep increasing your bets as you keep losing it. But this is a fallacy, because each trial is independent. So you may not get, even after 6 trials, you may not get your number. That is there.
Yes.
Yeah.
It's
So-
not even it's independent events. Every trial is itself independent.
I was so convinced that actually I believed it. Yes. First time when we lose it, don't lose heart. Double your bet. Next time, okay. Even if you lose it, triple your bet. Don't lose heart. At least you are closing. You are coming to the 6 trials. At least one of the 6 trials you should get. That's what probability says.
Yeah.
But it's not true.
But if they are
Very
independent,
interesting example, ma'am. Very interesting example.
very interesting, exactly.
But, yeah.
It is a gambler's rule, right? Gambler's rule, I guess.
It's called gambler's fallacy.
Fallacy.
Yes. So when you first learn about probability, we were told like that. When you make 6 attempts, at least one you should get 1 by 6, right? Your number. Okay, but it is not true. Let's say you are bet on number 3. Okay, somebody thrown dice 6 times. You think as per probability you should get your number 3 at least once. But it won't happen.
But yeah, it won't come. It may not come.
It may not come. Okay.
Yes, very true.
So it's very interesting example, and I think Kushid, you should prepare this probability subject very depth, so that you won't miss any interviewer questions. So I want to know where you have applied and have you got any calls yet?
No, ma'am, I have not got any call yet. I have applied in several IITs, Delhi. There are many IIT I have applied, ma'am,
Okay, nice.
including IIT Hyderabad also.
IIT Hyderabad.
But,
So what branches you are considering for?
ma'am, mainly core branches and one two interdisciplinary branches related to computer science.
Smart mobility.
No, ma'am, I haven't applied for that.
Okay. So core branches, if you are considering for communication, signal processing, so the probability, the questions
Yes,
they'll
ma'am.
definitely ask. So it's good. Okay.
Okay, ma'am.
In fact,
Ma'am,
in
can you
fact,
suggest me something from where to prepare for this?
Yeah, I'll
The
suggest you to prepare the random variable whole. And in next class, as suggested by sir, I will definitely deal with the distribution of random variables. I'll also revise my concepts of distribution of random variables and their applications, and the problems related to random variables. For example, how we will for example, x and y are two random variables which are distributed in Gaussian according to Gaussian distribution. Then what is the distribution of x plus y? What is the distribution of x square plus y square? Then what is the distribution of e power x? What is the distribution of e power x into y? These are the questions. What is the distribution of minimum of x into y, x of y? So these are the some probable questions you should prepare, especially this random variable, and also matrix theory, linear algebra, and signal system, linear system, nonlinear system, time causal, non-causal, and this analog then generally don't ask. To me, they didn't ask. But yeah, digital is very important. So digital and signal system, communication system. From these communication brands, I'm telling you. But from if you are also applying for VLSI, then I just suggest you to please prepare electronic devices, analog circuits. Yeah, analog with electronic devices, and one more thing, electromagnetic theory. I loved that subject at that time. So
Yes, ma'am.
yeah, so you
Okay,
can
thank you very much, ma'am. Actually, you have clarified a lot. I
So
will
have you
focus
applied
on
for
this.
VLSI?
Yes, ma'am. Yes, ma'am.
So your preference is VLSI only.
Ma'am, it is actually my top preference wherever I have applied, followed by communication theory and then this power electronics and all that.
Power electronics. Okay. Okay.
Yes, ma'am.
KG Krishna sir, you wanna say something?
yeah, but I found that probability theory is very important, madam. It is essential in many courses. I found in machine
Yes,
learning,
yes.
electronics, communications, and even general management. So I think I make an attempt at least master third time. I bought a lot of books. I think for every student should ensure, irrespective of the discipline. It is such a vital these days, particularly if you want to
Sir,
get into.
also machine learning. Machine learning is not even start without probability. It starts with
Yes.
probability, end with probability.
Yes,
So
linear algebra and probability is
yeah,
very important.
two subjects, linear algebra and probability. So most
I done this
probably
course.
in my next PMRFTA, I will take this course of applied linear algebra. So you people,
Okay,
if you
ma'am.
want to take that course, applied linear algebra by
So,
Aditya
ma'am,
Jagannatham sir. Ma.
excuse me, ma'am.
So
So,
you have
ma'am, from this mathematical part, I have to focus on linear algebra and probability, right?
sure, yeah. These two you please
Okay, ma'am.
prepare.
Got it, ma'am. Got it, ma'am.
Ha.
What I found is the best videos are MIT, this Gilbert Strang.
I have
Excellent
seen that. Yeah.
linear algebra. I
Ha.
think all over the world he's the
Best
go-to
teacher.
best
Kurshid, you please saw those lectures. I think
Gilbert.
it
Yes,
took
ma'am.
me around 10 days to cover that. But even if you are fast enough now, you can cover those lectures.
Sir, please spell that name for me.
Yeah,
Gilbert.
I'll type.
GILBERT.
I'll
G
type.
I
Okay, it is on YouTube.
It is on YouTube freely available.
Gilbert Strang.
Okay, and related to probability lecture, right?
Probability and I think he's famous for linear algebra.
Linear algebra, yeah.
Okay, thank you very much, sir. And thank you, ma'am, also.
Yeah.
Uh,
Gilbert Strang
okay.
is a god of I think matrix theory, linear algebra. So I also
Got it,
believe
ma'am.
that he is very, like, he explained everything very deeply and in a very good manner. Like, I also feel that Aditya Jagannatham sir is a god of for communication system.
Excellent, madam. He's the, no,
Yes, ma'am.
why I like his courses is he goes so coolly, systematically keeps writing so that we follow his trail of thought. Okay, I don't feel like referring any book after watching his lectures. I only make notes and I only look at notes. If I don't understand a concept, then only I go to YouTube. But otherwise, don't have to
Eh,
refer any book.
Yes. For me also, like, I feel so, because that's why I also mailed sir that I want to take your course. So I really feel he teaches very well. So if you want, anyone wants to learn communication system from
So,
zero to,
for example, I did communication systems 2 course last semester. Actually, this is the first time I'm doing communications that I did second level course itself. Okay, all this BPSK, QPSK, I'm able to understand without any background. Okay, so cool.
yeah.
That's why I continue to do PCA communication systems 1 and also signals and systems. Both I'm doing now in the current semester.
Okay, Abhishek Thakur is taking communication.
Yes. I think he's from IIT Hyderabad.
He's my friend. So, yeah, so he is also taking that course, and he teaches mainly gate questions, right?
Yeah. But anyway, I attend his tutorials also.
Okay.
So signals and systems is a very interesting, very important.
I'm very shocked that you're from different background. You're learning this subject. It's
Yeah.
it's
Yeah. Madam, I told you now. So I was curious about electronics. I bought some Wi-Fi, all these ham radio gadgets. So I wanted to understand how things work. So that's the reason that I'm doing all electronics courses. See, every time, for example, probability theory, I was not aware. So once I started doing this Aditya sir's course last semester, I got in touch with all this Gaussian. Then I read about probability on demand at that time. So I understood something. Now I understand something here. Maybe I understand something next semester. Maybe after 2 years, I fully understand probability. So we never understand in one go. I tell you that unless
yeah.
you
It's
you
very.
you,
So
you
you
by
teach in
practice.
Triple IT Hyderabad, na?
Yeah. No. I am in Hyderabad only. I teach a part-time BITS Pilani work integrated learning programs.
Bits Pilani, Bits
Yeah,
Hyderabad.
BITS Hyderabad. But I teach working professionals, MTech, part-time MTech. But I teach my own courses, that is software engineering, software project management, software testing, software quality management, and usability engineering. Nothing to do with any of these things.
Okay, software. Like,
Yeah.
my research is in 5G V2X, so if any
Yeah.
course is relevant to me, please let me
Yeah.
know. I'll also do that.
No, in IIT itself, in NPTEL itself, a lot of courses are there. No, some Kovil Pillai's course I took last semester. David Kovil Pillai, IIT Madras.
Okay.
So I passed. If I am able to pass, certainly you can enjoy that course.
No, yeah. Just for the sake of knowledge, like, right now, Tech Fest is was going on in Bits Hyderabad, I guess. So
Uh,
many of our friends were going to Bits Hyderabad.
yes,
So I
yes.
was also thinking about going. Like, it's
Yeah.
very far. IIT Hyderabad is located very
Yeah.
far from the
It is the
city.
other end of the city. You are
Uh,
in.
so
Yes.
it's very difficult to go out of the city.
Maybe I would
So
like to come once because I never came to IIT Hyderabad. Just like you.
yeah. You please, if you come, just let us know. Me and Abhishek Thakur, we both will meet to
Sure,
you.
sure. I stay close to Secunderabad area, railway station, Secunderabad.
Secunderabad. Okay. It's very far. It's 60 kilometer from the
Sure,
this one. 60 or 65, guess.
sure. Okay.
Yeah. So I think
Uh,
it's clear this mutually exclusive and independent events. So in the next class, I'll deal with some of the random variables. Also, could you please see the this joint distribution, joint random variable distribution like this one? So how joint probability distribution works? So if you define the joint distribution CDF, then CDF is nothing but this one, f of f of sorry f of x. This is small x. Inside it is small x. P of x less than equals to x. Okay. So this is CDF. Okay, and the CDF is also defined as minus infinity to infinity to x fx dx, which is fx is PDF. Yeah. So this is the basics of the random variable. How we can actually make a random variable to look using this probability distribution and the CDF. So in CDF we'll have the properties like this one. It should always be increasing function, monotonous increasing function, and their maximum value should be equals to 1. And for the PDF, their integration should be 1 because it is a probability. So how we will define the joint probability distribution? So f of xy inside of x of y, this is defined as p of x less than equals to x and y of y less than equals to y. So if two random variables are independent, their CDF also is equals to their multiplication. And CDF also, it has these properties, and CDF from infinity to infinity is 1. So you can see this is 1. From minus infinity to minus infinity it is 0. So these properties you have. From x to infinity it is f of xy, which is a function of x. From infinity to y it is function of y. So if you see the CDF function, you can visualize this. Now, yeah, this is what I was trying to tell. So if the sum of two random variables are there, then their distribution is their convolution. So suppose x and y are the Gaussian distributed random variable. Then the z is equals to x plus y. How the z will look like? Tell me how the z will look like. Means what is the distribution of z if x and y are Gaussian?
Ma'am, what we are doing here, we are multiplying them or adding them?
Here we are adding the random variable. Yeah, this is your question.
Okay, ma'am.
So when you are adding two Gaussian random variables, the output variable is also Gaussian, na?
How?
I don't know. I'm guessing. Okay.
If x, y are Gaussian, suppose mean of Gaussian distributed
Assume the same mean and same standard
with
deviation.
same mean mu and standard deviation sigma. Then how z will be distributed?
Yeah, this is assignment question. Maybe
Acha, this is assignment question.
yeah,
But and this is one of the question interview will definitely ask.
Yes. Yeah.
So I'll tell you. So basically, if this is the case, then f of z into z, which is a PDF of f of x into x, is the convolution of these two.
Oh, so addition variables becomes convolution in PDFs. Huh?
Yes.
It reminds me of the signal processing, Fourier transform. Convolution in time domain is multiplication in frequency domain. It's similar.
Yeah, it's similar. But
Can you elaborate little bit?
Yes.
Going over my head.
Okay. So suppose you have two random variables, and their sum will also be a random variable, because a random variable sum will also be a random variable. You know this property by the property of a function. So you know if you have two function, then their sum will also be a function. So the z will be also a function. Now I'm asking, if x and y are random Gaussian distributed with mean mu and sigma standard deviation sigma, then how the z will be distributed? What is the distribution of z? So in probability theorem,
Z is also Gaussian distributed. So what will happen to this mean and variance then? Mean and variance of Z with respect to this mean.
So let us call this. Do you know z expectation of x plus y? We saw from the expectation property. This is mu plus mu. This is 2 mu.
Okay. Mean will be combined.
Yes.
Standard deviation.
The standard deviation. How the standard deviation is calculated? This is expectation of z minus mu ka square sigma square. This is the formula for
2 mu, right? It will be 2
mu z.
minus 2.
Minus 2 mu square. Okay. So if you calculate this one, this z square plus 2 mu square, 4 mu square, sorry, minus 4 z mu. So using linearity property you were saying now?
Yes, ma'am.
Yes. So suppose this one is what? This one you don't know. So again we have to calculate x plus y square.
Madam, standard deviation is defined sigma square is equal to z minus mu z whole square divided by.
No. It is defined as this one. This divided it in the formula for Gaussian distribution.
Okay.
Like it's nothing but the value, the expected value by which the random variable varies with mu, with respect to mu. For example, here.
Okay. Differences between the.
Yeah. This mu, how this the random variable varies with respect to mu. So that's why you minus it and we square it, and we take the expected expectation. Then it is variance.
Okay.
Yeah.
Okay. Now let us calculate sigma square.
Yeah. So you know the constant property 4 will come outside, and this 4 mu will also come outside. Then E of z, expectation of z, and expectation of z, you know, this is what? 4 mu into 2 into mu, right? 4 mu square, and mu square is also, this is what I was telling you. Mu square is a mean, so mu square will come mu square. And this, let's calculate. X square plus y square plus 2xy. So you know x square. So if you don't know anything now, you just go by the formula, like by the basic. That's why. Minus 8 mu square. This 8. So I was telling you, if you have two random variable with the same mean and the same standard deviation, then these will be independent events. Why it will be independent? Because if you can see x and y.
Yes.
Yes, it will be independent.
So there is there a formula in the book for standard deviation of x plus y?
Yes.
Like,
If they yes. It has the formula. If they are independent, the standard deviation of if they are independent, then their standard deviation is simply their multiplication of this one.
Okay.
Sigma z square is equals to sigma x square plus sigma y square. But if they are independent, if they are not independent, then I think some values are there plus some, because these corresponds to independence of the event.
Okay.
I have to check that.
Okay. So similarly, we have expected value of x multiplied by y also.
Yeah. So
variable
these are mu into mu. I think it should cancel. Mu square minus 4 mu square. It should have some mu 4 here. It should cancel, and you will get sigma square, sigma y square. But I have to check where I'm getting wrong. So.
And similarly, what about x minus y? What about x?
Wherever the linearity properties come now, so it will be plus replaced by minus.
Minus. Okay.
Yeah.
Okay. But PDF is interesting. PDF is convolution. Okay.
PDF. Yeah, their PDF is convolution. We will see how it is.
This is the first time. It's interesting. I thought convolution is only in communication signals.
No. Convolution comes from the probability concept itself. So let's see how, like, where we are lagging. So x square plus, so sorry, here it's a square na, so 2xy 4 mu square. I think this should be z minus mu z square, z square plus 4 mu square minus 2 into 2 z mu, then e of z square into 4 of mu square minus 4 of z into mu, 8 mu square minus 4 mu square. This is x mu into 4 mu square. Where I'm wrong, I'm just wondering.
But the sum is it if it is not Gaussian, what it is, madam? X plus y.
Yeah, it is Gaussian.
It's
Because
Gaussian.
it will be the shifted, it will have the shifted mean of these two, sum of two means, and standard deviation somewhat sum of their values. It should come. I'll check with it where I'm lagging, but yeah. So if they are independent, then x plus y, f of x plus y, either capital and here small, x plus y, it will have mu of mu x plus mu y. And standard deviation I'll check and let you know in the next class.
So yes, I think this is interesting. So sum of two Gaussian variables, random variables, is a Gaussian. Okay.
Yes.
The mean can be combined together, x plus y.
Yes. So there it is a Gaussian.
Okay.
I'll check with it, like where I'm lagging. Maybe this formula or somewhere.
Because these kind of things are bound to come in the examination. Sure. Okay.
Yeah. These things will definitely come. So if you convolve these twos, x, can you tell me the convolution formula for the PDF?
Fx dot convol fy is equal to integral minus infinity to plus infinity fxx f of y minus tau. I don't know. Yeah. Fx of tau fy of y minus tau d tau. Yeah.
D tau.
I don't know. This is a communication.
T minus tau. T minus x tau y of t minus tau. Yeah, it was there, na, minus infinity to infinity. Yeah. D tau.
Yes.
So if you integrate it, so it's your homework because it will take time. I just want you to solve. By the way, it will come the Gaussian.
Okay. I was trying to understand, just on a side note, what is the physical interpretation of convolution? Okay. So I was just going through all over the net, YouTube, whoever. We understand as a layperson's multiplications, divisions, but a convolution operator is a very puzzling. Okay, what it is physically interpreting. Okay, it is so intuitive. We use it in communications. Okay.
Very true. Yeah. So, do you know correlation difference and convolution difference?
Yeah, correlation is it is also same thing, time shifted, right? Correlation means same signal with a tau shifted and then multiplied.
Yeah.
It looks like similar to convolution only.
Yes, it is similar to convolution, but I must say, so output of two functions, for suppose x and y are two functions are there, then their convolution x of t convolution of y of t is infinity to infinity x of tau y t minus tau and d tau. So you will get somewhat, suppose z, then you will get the terms at t.
Yes.
And if you calculate x tau y t minus tau, if you calculate this correlation, suppose z, then you will get in terms of tau.
Yes, yes. That is
Why?
because, correlation is not among two different signals. Correlation is same signal shifted by tau.
No, the two different also we can have. We are not bonding on that.
That is cross correlation, ma'am, right?
Yeah,
You
yeah,
have
that is
to.
cross correlation. But I must say
Ma'am,
that
there was some little bit difference actually between this correlation and
I'll
convolution.
tell
I
you
think.
what is the difference. I'll tell
Okay.
you. So I see whenever we have a system, a communication system. So in communication system, you will have input and output. So a output of a LTI system is represented by the convolution of the transfer function and the input. So here the term convolution comes. Here it is representing the output of LTI system. But whenever the correlation terms comes, so it is used to find the similarity of the two signals. So here we are trying to reverse the other signal and trying to find the similarity of two signals. Whereas convolution is always the output of a system, which is also a system, which is also
Yeah.
represented by system.
Yeah, the difference is the integration operator is T here in correlation, and in convolution is d tau,
Yes,
right?
yes,
Is that
yes,
is
yes.
that difference?
Yes, you can say this, but here the convolution always comes when we are talking about a system. So this is
Yeah,
convolution.
Ma'am, the mathematical expression is almost the same except from this variable is different.
yeah,
This
yeah,
tau.
yeah. Yes, yes. It looks interesting now. Okay, now, yeah. So in the communication, the output of that LTI system is in time domain T only.
Hmm.
But here in correlation, we get in terms of tau also.
Hmm.
Yeah, because the integration we are doing with reference to T in correlation.
Yes, 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 yes. One
Okay,
should
sir.
know this difference very well. You will have the one. You can also have one question out of this.
Yeah, the problem is in the MCQ they'll put all these things, you get confused. Tau, T, tau,
Uh,
yeah, yeah. So it's very,
okay.
yeah, yeah.
Ha.
Now I realize. Now I realize. I didn't know earlier. Now I realize. Thanks. Yeah.
Yeah, so you can see, and you should know their application also where we are applying this
Yeah.
to.
Yeah.
I think correlation.
Yeah. And autocorrelation means the same function. X of t into x of t minus tau.
Fourier trans. What is that? The Fourier transform of autocorrelation function is.
Fourier transform of autocorrelate.
Power spectral density.
Yes. So
Uh,
when you have the power spectral density of any signal, then if you take the inverse Fourier transform, you will get the autocorrelation function. And there we use correlation function. Whereas
uh,
in every other case, we use convolution to specify the system behavior. Like what is the output of a system and how it will behave, how it varies. So that is a convolution.
mm.
So I think this is what the difference between these two. And this thing I'll cover next again, x plus y. I think I have not covered very well. So this is pending. And
Okay. I think everything starts with signals in time domain.
e-
Starts with convolution, and from convolution we go into frequency domain multiplication, and once you hit transfer function, you go into frequency domain. It becomes a frequency response,
where is my pen?
and yeah, and frequency response can be expressed in z as a z domain, and yeah, if it is continuous, it's a Laplace domain. If it is discrete, it's Z domain. Yeah, yeah. So
Yes. So it's very good if you are preparing for it. So you can actually make a table out of that. where you apply jet transform, Laplace transform, and you just mention the difference so that you cannot forget it. Like
and I tell you, and another thing, madam. So because my study is all online only, I never referred to any books. But one confusion I get whenever I refer books, some people use frequency domain, some people use omega domain, some people use e to the power of j omega domain, some people use h of j omega domain. These notations, I cannot mug up formulas because some formulas in omega domain, some formulas in frequency domain. Is there any simple trick to remember for the examination?
Yeah, so I just tell you the in frequency domain I'll tell you omega f and have this relation omega is equals to 2 pi f. Otherwise e power j omega, wherever this e power j omega comes, then you just remember this, it is a transformation. So suppose some people refer h inside of e power j omega. So
no, but some people write, madam, h of j omega they write.
It is also written as yeah. So
is it both are same?
Both are same. Both are same.
Okay.
So it's just a transformation. It can be DTFT, DFT. So some people use different things, but you just remember one thing. It is a frequency domain transformation. So whenever you have this frequency domain transformation, for example, some people represent Laplace transformation by h of j omega. Some people refer h of s, because s is equals to sigma plus j omega, right? Sigma, if sigma is equals to 0, then you refer that to j omega. So it's matter of understanding, but you just remember one thing, that's the frequency domain transformation, and you will not have further confusion on that, I guess.
And another confusion I faced is the notation. Some people use analog digital frequency, small omega, capital omega. Some people use volta. For digital, they use capital omega. For analog, they use small. I don't know which is which Aditya sir follows. I think capital omega for digital. I think, right?
Yeah. Sir follows capital omega for digital.
If I refer books, they use small omega for digital, capital omega for continuous. So
one thing I just want to from you. So if you have x of t and you have transformation, either frequency domain transformation, or we can call Fourier transform. So how will you represent that? It is x of f or x of f?
Capital X of f. Yes.
Yeah, you should know this, because here the function is different. We cannot refer this small x to capital the same.
That I understand. But when representing in angular frequency, capital X of omega, which omega you use? That's where is that omega. There is another omega, right?
Yeah. Yes. So in analog, you represent this one as this one. In digital, you represent by small omega.
No, that in for example, in Aditya sir's one, it is reverse. I think. I don't
Yes, sir. Yes, sir.
So it is reverse, okay.
But in some books, what you said is right. They do.
Yeah. In BP Lighter, I think this is the case. In analog, we represent this as a capital like omega, and it's okay. Like it's just a representation, so you can just...
I my mind gets overblown because, for example, I have to mug up. No, it's not open book. For example, rectangular function in a time domain is a sinc function in frequency domain. I have to mug up that formula. Rectangular function in time domain, sinc function, is it a by pi or sinc?
It's sinc square, right?
F domain, which omega? So in omega is a different formula. In F domain is a different formula.
So rectangular function has sinc square in the frequency domain, but yes, for the exam point of view, you have to check with it, like what is following, because sometimes
we have to remember, right? We have to remember all that. That is the problem. Assignments anyway, I refer book on the internet.
If you are able to do the assignments, I think you will be able to do your questions, exams also, because it's very much similar.
Because the difficulty comes is we have to keep on referring to the formulas. Okay, the sinc function and because we get confused. The sync is a sync a omega by omega or pi n, I don't know all. So the that reference is something which we can do in assignments, but in examination we have to remember, right, all these formulas.
Yeah, very true. We have to remember the things.
That is mind blowing for me. Anyway, so
Yes, very true.
conceptually I know rectangular function is frequency domain is a sync function. In sync function in time domain is a rectangular in frequency domain. But questions won't be like that. They will give a time domain function rectangle. Sometimes some with different and ask in sync function it is a sync by a sync wn by n or a sync w by wn. Those kind of things.
Yes.
Puzzles us. Okay.
We have
So
to take care of that, I guess. When is your exam?
29th, I think. Yes.
29th, okay. So I think by next week, 15th or 15th, your all of your course materials gets over, right?
Yes.
15th, okay. So we'll have only, I guess, 10 days to cover all those stuff. But
Maybe one big sheet, madam, one formula sheet, important concepts written in one sheet to just before exam to remember. So
okay.
if it
I'll
if you find anywhere, that will be a lot of use. Otherwise, so every day I go through the net and this net and this Quora and Stack Exchange. I get lost and
okay. According to sir's notes, I'll try to make one formula sheet for you.
yeah.
I think it's over. Have
Important things we should remember. Okay, concepts I understand, but important things like
some we have to remember. It's very true, and yes, you have to remember. So the questions I'll deal in the next live session because I think week 10 you have already given, so it's okay. So I think we can end this class. So thank you for joining, all of you.
thank you very much, madam.
Uh,
So it's very
Thank you, ma'am.
interesting.
yeah, thank you so
Thank you.
much. Yeah,
Okay, excuse me, ma'am. Just one
yes.
second. Ma'am, you told me about this linear algebra, then probability, then there is signal and system. Then for VLSI, I have to prepare both these analog electronics and digital electronics, right?
Electronic devices, ED.
Okay, ma'am. And then EMFT also you told me, right?
EMFT somehow the favorite subject of some professors.
Yes, ma'am. Yes.
I personally don't have the interest in VLSI, so I didn't give much interviews on that. But I gave the interview of IIT Madras and IIT Kanpur. Yeah.
Okay, ma'am.
Then
Okay.
I got selected also IIT Kanpur, but I didn't went there because of my interest. So yeah, you go with the MOSFET. That diagram was there, na? MOSFET
Yes,
depletion
ma'am.
region. Uh,
Yes, ma'am.
MOSFET is one of the favorite topics, so prepare for
Yes,
that.
ma'am. Yes,
Uh,
ma'am.
and
Yes.
if you are preparing for this probability, then I think, this domain, communication domain, I think you will get definitely because you are taking the courses also. So
Yes,
it's
ma'am.
okay. All the best then.
Thank you very much, ma'am.
Okay.
Okay.
Okay.